Hey guys, welcome to derivatives and rates of change. We're going to start off today with the definition. The derivative of the function f of x with respect to the variable x. When we take the derivative, we have to take it with respect to some variable. First, this is the difference quotient. And the only thing we're adding here is the limit as h approaches 0. And I guess the question would be, why is that important? Well, here, I'm going to draw a picture over here. Okay, so let's say that's the picture of my graph. I'm going to pick a point over here for x, and we'll call this point x plus h. And so basically we have this point is x comma f of x. And this point right here is x plus h comma f of x plus h. If I were to want to use just the difference quotient without the limit, if I want the slope of the line that connects these 2 points, so those are 2 points. How would I find the slope? Well, I would say the slope is equal to y2 minus y1 over x2 minus x1. And for here, we have y2 is f of x plus h minus y1, which is f of x, over x2, which is x plus h, minus x1, which is x. And we can see that what this gives me is f of x plus h minus f of x over, and then the x's are going to cancel, and we just have h. So notice here what I've got just from the difference quotient without the limit is I have this function, which is the slope of the line. The derivative measures the slope of a graph at each point. We're looking at the change in y over the change of x, which again is our slope. We also call it the average rate of change. Again, draw a graph. I'm going to draw it a little bigger here. And let's see, we'll do this. Okay. And before, we just picked 2 points. So let's pick a point here, and we'll call it x. And I'll pick a point here, and I'll call this x plus h. The difference between these two is h. Like, say, for example, here I have x is 1, and here, this point here is 3. Well, we would know h is 2. So they'd be that distance apart. I have, again, if we just redraw it, I have this point, and I have this point, and this time the slope is going to look a little different because I picked different points. So now we can tell we have a negative slope, and we can see that if we just take our f of x plus h minus f of x over h, we would get the slope of the line. But what if I want to actually find the slope of the line at a specific point? Like, for example, I want to find the slope of the line at this point. And when I say at that point, I mean just this point, not between 2 points. If I wanted to find the slope of the line at that point, this right here is called a secant line. It goes from one point to another point on the curve. But I can also want to find what we would call a tangent line. And a tangent touches the graph at exactly 1 point on any curve. But we can see that if we make h 0 and we just have this 1 point, we're just going to get 0 over 0. When I add this limit as h approaches 0 of f of x plus h minus f of x over h, well, I can see that I'm dividing by 0. And since I only have this 1 point, which is x comma f of x, then I would just get 0 over 0. So the question is, what do we do? That's when we start using derivatives. Let's say this is x plus h. Because what we've done is decrease the distance of h, and h is now getting closer to 0. If this is my point, and this is my point, now notice I have a secant line, and it is looking a lot closer to my green line, which is my tangent line. And as I move closer and closer, what is happening here, as you can see, is we have 2 points that are really right next to each other, because we're saying h approaches 0. We're not saying h equals 0. We say that it approaches 0. Imagine I blow this point up right here, and I make it 1,000 times as big. Really, what I end up with is a straight line where this is x and this is x plus h. And because I've blown it up 1,000 times, they're really pretty much right next to each other. I get my slope of the line. So basically, that's what the derivative is. The derivative is the slope of the line that is tangent, and tangent means it only touches in one place, only touches in one place, to any curve at some point. And we can see, I'll just do this quickly. Let's say I have a parabola. I can see that if I pick this point, then the derivative or the tangent line would look something like this. So it's definitely got a negative slope. But I could also pick a point here and find the tangent line. And now we can see this has a positive slope. So we can see that depending on where on the curve I pick a point to find the slope of the line that's tangent, depends on what point I pick. If I pick a point down here at the vertex, my tangent line basically is horizontal. When we find the derivative, we're finding it at 1 point. We're saying that the derivative is the same as the instantaneous rate of change. Rate of change at that point. So it's at this point, at this point, at this point. Whereas here, If I pick this secant line, well, it's more of an average rate of change. Whatever that value, whatever these two values are, this is going to give me an average rate of change. But once I pick the point and I say the limit as h approaches 0, then actually what I've got is an instantaneous rate of change. Here we have time, and we'll call this time in hours. And here I'm going to have distance. And we can call this distance, we'll call it miles. You can call it anything, you can call time seconds, you can call distance centimeters. It doesn't really matter, but we're used to using miles and hours, so let's say miles and hours. Let's say I start here. I get in my car and I'm going to go to Orlando. And let's say Orlando is 200 miles away. Let's be 1, 2, 3, 4. In 4 hours, I'm going to go 200 miles. The average rate of change, if I connect these 2 points, since this is 0, 0, and this is 4, 200, then my average rate of change would be the slope of this line, which would be 200 miles divided by 4 hours, which would be 50 miles per hour. If you just saw me leave and then I called you when I got to Orlando and it was 4 hours later and I drove 200 miles, we can see that I would have been going 50 miles an hour. But that's not actually what happened. So let's talk about what happened on our trip. Well, we obviously got in our car, and for the first hour, I went, this is 100, let's make this 50, and then let's make this 150, okay? In the first hour, I drove 75 miles. So how fast was I going? I was going 75 miles an hour. And then we got an hour in and I had to stop for gas. So I stopped for gas and then I went into the store and I got something to drink. And it took me, let's say it took me a half an hour before I got back on the road. So this is 1.5. And I didn't go anywhere. So I'm still here at 75 miles, right? And now all of a sudden I get back in the car and I want to make up some time. At 2.5 hours, I get to 150 miles. So now I only have 50 miles left. So what am I going to do? I'm going to slow down because I'm just going to get off the expressway. I'm just going to take a smaller road. For the last hour and a half, let's say that's where I went. What's really happening here? I know that the average rate of change is 50 miles an hour because it took me 4 hours to go 200 miles. But here I was going 75 miles an hour. And here I was going 0 miles an hour, right? And then again, I picked up to 75 miles per hour. And then on the last hour, it took me, actually the last hour and a half, it took me took me an hour and a half to go 50 miles. So let's say I was going about 30, let's say I was going 30 miles an hour for the last part. It's a little more, but just so you understand, what am I telling you here? I am telling you that the average rate of change was 50 miles an hour because that's how long it took to get there. But the other thing I'm saying is that the instantaneous rate of change, ROC will stand for rate of change. So the instantaneous rate of change here would be it would be 75 miles per hour between 0 and 1, between the interval 0 and 1, and then 0 miles per hour between 1 and 3/2, and so on. And what does that mean? Basically, it means that if you looked at my speedometer for the first hour, I was going 75 miles an hour. And then I stopped. So if I just went from 0 to 1 hour, my average rate of change and my instantaneous rate of change would be the same, but it's not, because I'm changing speeds. And imagine also if I was changing speeds, but it was even more curved, which is probably more true, that it's more curved. My instantaneous rate of change is what's on my speedometer. And obviously, I'm not going to go from 0 to 75 miles an hour that quickly. So everything will be a little more curved. I'm not going from 75 miles an hour to 0 in 1 second. This would be a little more curved, this graph, but it doesn't really matter. I think what I'm trying to do is just show you the difference. If I have distance and time, or if I find the slope is going to be miles, because it's the y is in miles over hours. I can say that the derivative here, let's just call it the derivative, because we're talking about the instantaneous mostly. That's what this section's about. The derivative would be the change in y over the change in x. And we can see that that is going to be velocity. Miles per hour is velocity, or speed. Velocity can be both positive and negative, but speed is always positive. We're going to talk about the difference quotient. So the difference quotient, as we've already said, is the average rate of change of y, because I have y, with respect to x, because I have x. I could call this d, and I could call this t, and then it would be the average rate of change of d with respect to t. So that's basically what that means, and can be interpreted as the slope of the secant line PQ is the blue line. So this is the average. We can see it's the average because their x1 and x2 are far enough apart that it's not going to be exactly the same as this right here. So the average would be the same as the secant, and that right there would be the instantaneous or the tangent line. So we can see that that pink line is the tangent line at that point on the curve right here. Hopefully you can see that as I move this point Q closer and closer to P, the secant line is going to get closer and closer to the tangent line. The limit of these average rates of change is called the instantaneous rate of change of y with respect to x, which, as in the case of velocity, is interpreted as the slope of the tangent to the curve y equal f of x. This right here, remember those 2 points are getting closer and closer together. We call it the derivative. That is one type of notation for derivative. And I will show you a few more in this slide presentation. And notice it's saying it's the instantaneous rate of change because we have h going to 0.